Hey everyone, Mr. Shouter here to take a closer look at the definite integral that we just examined in the previous video. Let's take a dive in. Let's look at the notation of the integral carefully. So let's start with the bounds. So the lower bound is known as a, and the upper bound is known as b. That's the region a to b that we are taking a look at squeezing those rectangles in, or considering the area in. The elongated s is known as your integral symbol. The function f of x that you're taking the integral of is known as the integrand. It's very similar to a radical. The thing inside a radical is known as the radicand. And then the d represents respect, and the x is the variable of integration. That's the variable that you're taking the integration with respect to. Once you have solved the problem, you've basically evaluated the integral, and you'll always get some number. Okay, some numeric value. As long as you're integrating with upper and lower bounds, the answer will always be a number. One last thought. It's very important to understand that the variable that you're taking respect to of integration doesn't actually matter. That variable could be anything. In fact, we actually call it a dummy variable because it doesn't matter. So you could use a t, you could use a u, you could use an x. It really doesn't matter. What does matter, though, is that your respect matches the variable that you are taking integration with respect to. Okay, so the only thing that matters is that letter matches. So the dt matches f of t, the du matches f of u, and the dx matches f of x. As far as that goes, though, it doesn't ever have to be any one of those variables in particular. Example 1. Let's take a look at how old notation would equate to new notation. So it says the interval is evaluated from -1 to 3, so I'm going to automatically start with my integral symbol and go from -1 to 3. Then it says partition to n subintervals of equal length, delta x equals 4 over n, let m sub k denote the midpoint of the k subinterval. The nice thing about the new notation is you really don't have to read any of that. I shouldn't say that, but it doesn't really make too much of a difference in regards to what I'm trying to do in this particular problem. All I want to do is basically set this problem equal to the normal integration problem. This delta x, as we saw in the first video, is going to translate to our respect. Okay? And then anywhere you see this m sub k, that's the variable x. So I'm just going to write the polynomial 3x squared minus 2x plus 5, because the 5 doesn't have a m sub k, so there's no need to put an x with it. It's up to you if you want to put this all in parentheses to separate that from the dx, but it's not necessary. Sometimes we use a lot of different functions inside the integral, and it's sometimes cleaner to have the dx outside everything, but it's not necessary in this problem since it's just a simple polynomial. Okay, let's talk about the area under a curve as a definite integral. What an integral is designed to do is to measure, to actually add up all the area accumulation under a curve. So long as f of x is non-negative, meaning always positive, the area under the curve is just simply the integral from a to b of f of x dx. If the area is negative, then you just negate that number, and then you get the integral of a to b of f of x dx. So essentially what an integral is designed to do is to measure the net area. All the positive area, take away all the negative area. So all the area above the x-axis minus all the area below the x-axis. Example 2 says the integral from 0 to pi of sine x dx is equal to 2. We can go ahead and use that fact that from 0 to pi the integral, the area is 2. Since we know that sine is odd, I can also conclude that if this is 0 to negative pi, that this is the same area but negative, so it would be -2. So the first question says to take the integral from pi to 2 pi of sine x dx. So if I extend my curve down to here to 2 pi, I know that this region is -2 as well. So just from pi to 2 pi would just be that -2. So the answer there would be -2. So we'll put a square around it. Okay, number 2 is asking the integral from 0 to 2 pi of sine x dx. Well, the integral from 0 to 2 pi, oh, I don't know why I just erased that. I needed it. I always thought we were doing negative pi to pi. The integral from 0 to 2 pi would be this positive 2 added together with this -2. So the integral would actually be 0. Because remember, what the integral is doing is it's taking positive above the x-axis as positive and below the x-axis as negative. All right, let's try the next one. Let's just get rid of all this stuff now. It's getting too messy. Okay, the integral from 0 to pi over 2 of sine x dx. Well, pi over 2 is right here. So I know that the integral from 0 to pi over 2 is going to be exactly half of the integral from 0 to pi. And so I know that this is going to be 1. This is going to be 1. How about number 4? Number 4 is a little weird. It says the integral from 0 to pi of 2 plus sine x dx. 2 plus sine x dx. Well, picture we drew a new curve, a new sine x. And we started it at y equals 2. So this is like y equals 2. And now I started my sine x, and I'm going to go from just 0 to pi. So I'm just going to do one loop like that. Okay? And this is 0, and this is pi. And I know that up here, the integral is still 2. So this region right here is equal to 2. But I actually have to add this, and we'll use like a pink, this rectangle, right? So the area of this rectangle also needs to be added to the integral. So that is just going to be, it has a height of 2, and it has a base of pi. So it has an area of 2 pi. So the integral in number 4 is just going to equal 2 plus 2 pi. And that's all you would need to do. And so you can try the rest of these on your own and see if you would be comfortable solving them. Let's try this example. It says the integral from 2 to 4 of the absolute value of x minus 3 dx. Well, I know enough about the absolute value of x to graph that. Let's graph this. So this is the absolute value curve moved 3 right. So here's 1, 2, 3 right. And this is now the corner point. And I know then that the graph just kind of has a slope like that and a slope like that. And I'm going from 2 to 4. So essentially the area that I need to calculate is the area from here to here, and then from this focal point, the corner point, to 4. Well, it's just 2 triangles. And I know the height of this triangle is 1, and I know the base is 1, and same thing over here. And so the area of each of the triangles is just, area is 1/2 base times height, which is 1/2. So each of them, and I'll put it in like a nice green, each of them have an area of 1/2. So then the accumulation of area, they're both above the x-axis, so they're both positive. 1/2 plus 1/2 would be 1 whole, or letter A. Let's take a look at integrating constants. So if you take the integral of a constant, it's actually just equal to the constant times the difference of your bounds. And let's take a look at a picture as to why. So suppose we have some constant c, like it could be 3 or 4 or 5. The area of this rectangle formed is just equal to the constant height c, which represents the height of the rectangle, right? This distance is c. And then multiplied by the width of the rectangle, which is just b minus a, assuming that it's not snug on the origin. Otherwise, it would have just been b. So the integral of any constant is actually equal to the constant value times b minus a, which is the difference of your bounds. Suppose the rectangle is below the x-axis, it would just be the negative version of that, negative c times b minus a, which the formula still applies. We didn't specify that c was positive. It's just equal to c times b minus a. One more interesting fact, if you're doing a function that's discontinuous, it can actually be integrable. You could actually calculate the area under the curve. Let's do a throwback to the absolute value of x over x, one of our more famous functions we looked at earlier in the year. If you recall, it just looks like positive 1 to the right of 0 and negative 1 to the left. So if I asked you to integrate it from negative 1 to 0, you'd integrate it from here, negative 1, and then, sorry, I said negative 1 to 0, negative 1 to 2. So here's 1, here's 2. So if I split this up into rectangles, I'll do this one in red. So here's the rectangle here. This has an area of simply 2 times 1, which is 2. And then the rectangle down here is right here. And this one has an area of 1 times 1, which is 1, but since it's below the x-axis, it would actually have an area of negative 1. The integral is designed to add the areas together. So the integral of negative 1 to 2 of absolute value of x over x dx is equal to 2 minus 1, which is 1.